Today I want to talk about section 4.2, the mean value theorem. Okay, you might ask yourself, calculus is hard enough. Do we really need a mean value theorem? Well, mean here is talking about the average. So this is the average value theorem. And this is the third of the three value theorems. The first one was in section 2.5. That was the intermediate value theorem. And the second was in section 4.1, the extreme value theorem. And today we're looking at the mean value theorem. So they all start with the same hypothesis. If f is continuous on the closed interval. And some of them have additional hypotheses, but then the conclusion is also the same. Then there is a C, meaning at least one, in, now this varies a little bit. Sometimes it's the open interval. And for the extreme value theorem, there's no other hypotheses. And in this case, it's possibly the closed interval. It's in the closed interval rather than the open interval. Here we'll have an additional hypothesis. Okay, so again, at least one. This is going to be open interval. So they all have the same basic setup, that we have the same hypothesis. If f is continuous on the closed interval, and the same conclusion. Then there's a C, at least one in the interval, so that f of c equals, and so f of c, this is the value. The value is the y value, f of c, f of c. Right, so what are we saying about, so for the intermediate value theorem, we have an additional condition. An additional hypotheses. So what intermediate here means between. There's a value in between. So the conclusion is n, f of c is n. There's a point where the y value is between f of a and f of b, and you can choose your number between there. You're gonna hit it. The extreme value theorem was the one we did just last section. It says there is a place where you have the absolute min, and this is really a very good value. It's an extremely good value because we also get a second value for no extra cross. So there's a C and there's a D, also at least one, in the closed interval. So we get the absolute min and the absolute max. So that's an extremely good value. 2 values for the price of 1. Here the additional condition, there is an additional hypothesis for the mean value theorem. We need f to be differentiable. Remember, that means the derivative exists. And it exists on the open interval. Then there's a C, at least one in f of in the interval, so that, okay, so this is actually talking about not f of C this time, but rather the derivative of C will be will look like this. Okay, so here are our 3 value theorems. They'll have the same, at least one of the same hypotheses, that f is continuous on the interval AB, closed interval, and they have similar conclusions, but slightly different versions. Sometimes there's an additional hypothesis. For this one, we get an additional conclusion. The topic is the mean value theorem. And what is, remember I said mean means average here. It's not a nasty theorem. It is talking about some kind of an average. So what, maybe not completely clear what the average is, but hopefully you can recognize this kind of thing, f of b minus f of a over b minus a. That is something similar to what we saw. Actually, when we calculate derivatives, we do something like that. You remember when we first looked at derivatives, we were thinking about f of x minus f of a divided by x of a, x minus a. So that's pretty similar kind of idea. So what's going on here? What does this f of a minus f of, maybe I'll write it over here, rather f of b minus f of a over b minus a. This is what we're seeing on the right hand side. We're saying this, the derivative f prime of c is equal to that. And what is that? Well, let's put the y values in. F of b, f of a, f of b minus f of a, that's the distance here, the distance between those 2 points. In other words, that's the change in y. So what we have on top is the change in y. And on the bottom, we have the change in x. B minus a is the difference between the 2 points over there. So this is a slope. This is the change in y over the change in x. And what is it? It's the slope of the secant line. Yeah. So we're saying something about the slope of the secant line. So I don't know if you remember, but this is also the average rate of change. Do you remember in the very first section in the calculus part, we talked about dropping a ball from the CN tower And we said the average rate of change, we can calculate it using the average velocity, right? The average velocity is related to the secant slope. So this is why it's the mean value theorem, because we're getting a value for the mean rate of change. And what value is it? Well, it's f prime of c. And what does that mean? The derivative at c, that's the slope of the tangent line. So we're saying that at least once in here, we must have the tangent line parallel to the average rate of change. Somewhere in the interval, the tangent slope is the average slope. That's what the mean value theorem is saying. There has to be at least one point. There might be another point. Looks like over here, there's another place where that happens. But what these value theorems are saying, there has to be at least one C that works. There might be more, but at least one. Okay, so what is this good for? Well, it's good for catching speeders. So you might know that when you're driving on the highway, you sometimes see the speed is checked by aircraft. How do they do that? So they have a line on the road, and they can't see what's the time when you go past that line, and then another line on the road, and they find the time when you go past that line. So that gives them a change in x, the change in position. So they know the distance between those two lines, and a change in time. So they can get a velocity. They can get your average speed over that interval. And if your average speed is over the speed limit, that means at some point during that time, you were going too fast. Your speed, your instantaneous speed, must have been more than the speed limit if you're looking at the average. If you get the same as, if the average rate is too fast, then it definitely at some point you were going too fast. So this is the idea that they use to catch you when you're driving too fast on the highway. Actually, the usefulness of this theorem is not so great, but what makes it useful is the way that we relate. So maybe I'll just remind you that what's going on here is the big conclusion is the slope at C is going to be the tangent slope at C is going to be the average slope. That's the conclusion for the mean value theorem. We'll find at least one C where the average slope agrees with the slope of the tangent at C. So this is actually not that useful in itself, but what makes it important or useful is it gives us a way to take values of the function, rather to take knowledge about the derivative and make deductions about the value of the function. So far in this course, we've been given a function, we're trying to find the derivative, but now we're going to go the other way around. What if we know something about the derivative? What does that tell us about the values of the function? So for example, if we know the derivative is 0 for some interval, what does that tell us? What kind of a function is it whose derivative is always 0, right? 0 means horizontal slope. The slope is always horizontal. Well, I'm moving it around a lot, but actually it can't be moving that much, because if we know this is 0, right? If the slope is always 0, then it's including at our C, it would be 0. How do you make a fraction 0? the top has to be 0. So this is saying f of a and f of b are always the same. Whatever little interval you look at within there, the y values are going to be the same at the two endpoints. So all within this interval here from a to b, all the endpoints are always giving you the same y value. So the only way that that can happen is if your function is constant. It's just a horizontal line. The only way that you could always have your derivative be 0 is if what the function you're looking at is just a horizontal line, a constant function. Okay, so this is the utility of the mean value theorem. It gives us a way to take things we know about the derivative and deduce information about the function. Okay, so here's a corollary, or this is an immediate consequence of the mean value theorem. Actually, it's really a corollary to the theorem 5 here. If the derivatives of two functions agree, so suppose we have a function f and a function g that have the same derivative throughout an interval. So what does that mean? So what you can deduce from that is the functions, they may not be quite the same. Of course, if they are the same, then that would be true. The derivatives would be the same. The f and g don't have to be exactly the same, but the only difference is a constant. So basically f is g shifted by some constant c. So we just take the whole g function and say c is positive, we move it up by f. So we could have the same derivative if they're the same function, but otherwise f is just g shifted up by a constant. So how can you see this? How does this follow immediately from the earlier theorem? Think about f minus g. Think about the function f minus g. The derivative of f minus g is going to be 0, because the derivative of f, remember the difference rule, the derivative of a difference, it's the difference of the derivative. So the derivative of f minus g would be f prime minus g prime, which is 0 all the time. So f minus g, the derivative is 0 all the time. F minus g is a constant. F minus g is always equal to c. So f is g plus c. That's the big idea here. Okay, so if we know something about the derivative, we can figure out something about the function. That's the big use of the mean value theorem. That's how we're mainly going to use it. So in the exercises, you'll be asked to, and I'll work one example for today to show you how this plays out. And the examples are more based on the mean value theorem statement, but the way we actually use the mean value theorem is more about, if we know something about the derivative, we can find something about the function. So here we're supposed to verify that the function f satisfies the hypotheses of the mean value theorem. Then find all the c's. The mean value theorem says there will be a c, at least one, but there might be more. So here we're trying to find them all. So what is the function in this example? The function is x cubed minus 3x plus 2 on the interval minus 2, 2. So what are the hypotheses that we need to check? There's two hypotheses. F should be continuous and F should be differentiable. Well, what kind of a function is this? Because we know a lot of our functions are continuous, right? Actually, we said pretty much everything's continuous. It was easier to talk about what's not continuous. What's not continuous is the brace or the piecewise defined functions or the Grace integer function. So this is a polynomial, so it is continuous on the interval. It's actually continuous on its domain, right? That's what we said. Most functions are continuous on their domain. And what's the domain for a polynomial? It's all reals. This is defined everywhere, so that's okay. So let's just write that down. F is a polynomial. So continuous on its domain, but for a polynomial, the domain is all the reals. And how do we show? We were supposed to check the two hypotheses. So that's the first hypothesis. How do we show it's differentiable? Well, the easiest way to show it's differentiable is to calculate the derivative. So the derivative of x cubed, use the power rule, 3x squared, and the derivative of 3x is 3. The derivative of 2 is 0. Okay, so the derivative is also a nice polynomial, especially the domain is all the reals. So this function exists on -2 to 2. Actually, we just need it on the open interval, but this one exists for all the real numbers. So F is differentiable on the open interval. This is the second hypothesis that we need. So we verified the hypotheses. Now we need to find the c's. So remember, what's the equation? F prime of c, which we just figured that out. This is 3c squared minus 3. Has to be f of b minus f of a over b minus a. That's the conclusion for the fundamental mean value theorem. So we need to find f of b, which in this case means f of 2, and we need to find f of -2. So what is that? F of 2, you can just put in 2. What do you have? 8 minus 6. So 2 plus 2. F of 2 would be 4. F of -2, very similar, but now we're going to have a -8 plus 6 plus 2. So that actually ends up being 0. And on the bottom, I wrote this wrong because we're supposed to take the difference. So 2 minus -2, because b is 2 and a is -2. So this is also going to give us a 4. So this is going to be 4 over 4 or 1. So we're trying to see where is 3 squared minus 3 equal to 1. In other words, we want 3c squared to be 4. We want c squared to be 4/3. So there's going to be two places where this happens, right? Because when you take the square root, that gives you two options, and 4, the square root of 4 is 2, so we can write the answer like this. So this is the answer, but let's look at the drawing, because this is supposedly going to tell us something about the mean value or the average value. This is giving us the average slope. The average slope is actually 1. That's what we're seeing here. So let's try to draw this. This is a cubic. And we just worked out the value at 2 is 4. And the value at -2 is 0. And what's the value at 0? That's also easy for a polynomial, right? The value at 0 is 2. So something like that. And turns out it's also 0 here at 1. If you do the calculation, so it's going to look a little bit like there. Okay. And what we're saying is the average slope here turns out to be 1. We figured out because it was 4 over 4. And there's going to be two places where the tangent slope is the same. One is at -2 over root 3. And another is at 2 over root 3. Okay, so this is 3 parallel lines because they all have the same slope. Okay, so that's the big idea of the mean value theorem. So just to review, today we are looking at the mean value theorem, but this is the third of the value theorems in this course. They all have the same hypothesis. F is continuous on the closed interval AB. Sometimes there's an additional hypothesis. Today there is. F should also be differentiable. Then they all have the same kind of conclusion. There is a C, at least one. So that's the value. The value refers to this F of C, or in this case today, we're going to look at the derivative at C. And what do we say about the derivative? It's the average or the mean slope. This FB minus FA looks a little bit like what we did for the derivative, f of x minus f of a over x minus a. That represents the secant slope, the slope of the secant line, which we also can interpret as the average rate of change. And that is agreeing with the tangent slope. I guess I forgot to say this. This is the tangent slope. So at some point, the secant slope is going to exactly equal the tangent slope. That's kind of similar, but a little different, right? For the derivative, we say the tangent is the limit of the secant slopes, but here we're saying there's going to be actually a place where they're exactly the same if we have these two hypotheses, if the function is continuous and differentiable. There's going to be a place where the derivative, which is the limit of the secant slopes, actually agrees exactly with one of the secant slopes. This is, fun to do little calculations, find the C, but usually the main use is if we know the derivative, we can figure out something about the function. For example, if we know the derivative is 0 all the time, that only way that could happen is if the function is just a horizontal line. The only way you can get the slope to be 0 all the time is if you have a horizontal line whose slope is 0. And immediate consequence, if two functions have the same derivative, they don't necessarily have to be exactly the same function. But if you think about f minus g, the derivative of f minus g would be f prime minus g prime. The derivative of f minus g is 0. So f minus g has to be constant. So in other words, f is just g plus a constant. F is g shifted up or down. If you think about shifting the curve straight up and down, nothing's going to change about the slopes. The slopes are still going to have the same values at each x. And then we looked at a little exercise for a polynomial, a cubic polynomial, to see a concrete example of how the average slope is equal to the tangent slope. The secant slope is equal to the tangent slope at least once. In this case, it actually turned out to be twice.